Earlier we had defined the regions for a homogeneous dam. Now we are going to create the material properties. We are going to assume that it is a silt, and so we have to define the volumetric water content for silt, and then we are going to estimate the hydraulic conductivity from the volumetric water content function, and then we are going to have to define some boundary conditions and apply the boundary conditions. So we have a homogeneous dam, and we have a reservoir on the left-hand side. So we are going to have to define a boundary condition on the upstream face, and then we are going to have to define a boundary condition on the downstream face, and look at the results and show you how to interpret the results. We are going to use a sample function that comes with the SEEP software, and we are going to use the sample function for silt, and we're going to make the porosity 0.45. In other words, the volumetric water content at a zero pressure is 0.45. Then we are going to estimate the conductivity function, and we're going to say that the saturated hydraulic conductivity is 1 times 10 to the minus 5 meters per second. Going to GeoStudio, then we will open up SEEP 04. Once you have opened the file, this is what you should see, and basically it is a drawing of where we left off when we drew the regions for this problem. To begin then, we will say key in hydraulic functions, volumetric water content function. We add a function, and let's name this silt water content. The type is a data point function. The type is a data point function. Then we will click on Estimate. And you can see that the estimation method, there are several methods available. We are going to use a sample function as our estimation technique. And then from this drop-down list box here, we have several functions. We have a function for clay, silt, silty sand, sand and gravel. We are going to select silt as our sample function. And our saturated water content, we said, was 0.45. Clicking on OK produces a function. Click on Edit Data Points. So here is our sample function for silt. It's the silt volumetric water content function. Notice that we specified the porosity or the water content at zero pressure as 0.45, and we have an air entry value around about 2 to 3, 4 kPa or something like that. Now we have defined our volumetric water content function for the silt. Next, key in hydraulic functions, hydraulic conductivity function. We add a function, let's call it silt K. The type again is a data point function. We will estimate the function. We will use an estimation technique known as Van Genooten, or we say often Van G. There are other methods, but I won't spend time on them here. Then we need to say we are going to use the volumetric water content function that we had defined previously. This is the volumetric water content function we had defined previously. Our saturated conductivity is 1E minus 5. And the residual water content is generally about 10% of the saturated water content. In this case, let's say it's 0.05. It's very close to 10% of the saturated water content. Clicking on OK. Once again, we are in an arithmetic scale. Click on Edit Data Points. And here is our hydraulic conductivity function for the silt. And we have estimated this function from the water content function. Next, click on Key N Materials. We have to create a material by clicking on Add, naming the material Dam Silt. And now we have to select a material model. We expect to have an unsaturated zone, and therefore we need to select a model that includes saturated, unsaturated flow. We have the material, and this material has a hydraulic conductivity function. We can select it from this drop-down list, the function that we had just defined, silt K. We do not need the volumetric water content function for this analysis because it is a steady state analysis, but we already have it defined. We might as well attach it so we get some more information, but this function is not part of the solution because it is a steady state problem. We now have defined our material. Next, click on Draw Materials. And notice we have a drop-down list here. The drop-down list only has one material, which is the silt for this homogeneous dam. And when we are drawing the materials, we can draw the material on a region or a line. In this case, we want to draw it on a region. And notice that the cursor turns to a small square as soon as I'm over a region. We can click on each of the regions to attach the material to the regions themselves. We can turn off the mesh. We had talked about that earlier. To those of you who were part of the Slope W session, you will notice the green ground surface line. In this particular problem, we do not need the ground surface line. We can uncheck that so it is not shown on the drawing. We have our regions. The material has been attached to the regions. Next, we need to define boundary conditions. Let's start with defining the boundary condition that represents the full supply of the reservoir on the upstream face. We have 8 meters here, So what we want to do is we want to define a total head boundary equal to 8. Say key in boundary conditions. SEEP-W always comes with some defaults. You can ignore the defaults for the time being. Click on Add. Call this Upstream Face. It's a total head type boundary condition. It will be a constant, and the action is 8 meters. We can select a different color. Let's select a green or whatever color you prefer. The next step, after defining the boundary condition, we can define it on the edge of the region. We say draw boundary conditions. From our drop-down list, we have an upstream boundary condition. We are going to apply the boundary condition to a line. And once again, when my cursor gets close to the region edge, notice it turns into a line, and I now have defined this boundary condition on a line. Now the boundary condition has been applied above the reservoir level. This was really not the intent, so we have to subdivide the upstream face or subdivide the region edge into 2 parts so we can appropriately apply the boundary condition. Turn on Snap to Grid, making the grid spacing a 1/2 meter by 1/2 meter. To subdivide the region edge, we say draw a point. And we're going to draw a point on the region edge face at the elevation of the reservoir. Notice here that the y coordinate is 8 meters. Sorry about that. Draw points, I will repeat it. And I right mouse click. Let's turn off the boundary conditions, and we now see we have a point here. Displaying the boundary conditions again, I can remove the applied boundary conditions on the upper portion of the region edge by draw boundary conditions, remove, and when I click on this portion of the region edge, I remove the boundary condition. So I had to subdivide the upstream region edge so that I could apply the boundary condition only where the reservoir contacts the dam. Turning off Snap to Grid, I need to do one other thing, and that is to say something about the downstream face. In this case, we will model the situation without the tow drain, and consequently we expect there to be a seepage face here. The line of zero pore pressure will come in here something like this and then come asymptotic to the downstream face. My problem is I don't know what the size of the face is. And consequently, I cannot specify a head because I don't know the size, and I cannot specify the flux because I don't know the size of the seepage face. I don't know how to subdivide the seepage face to apply an appropriate boundary condition. So SEEP-W has a special type of boundary condition where we say the flow is 0, but it will be a potential seepage phase. Say draw boundary conditions, key in. We have already by default given you a potential seepage phase boundary condition. Now this is incredibly important here. Notice that a potential seepage phase is a total flux boundary. The total flux in this case is 0. However, we have checked this option here. It says to SEEP-W, you iterate and flip back and forth between Q and H until you find the proper size of the seepage phase. So SEEP-W goes round and round and goes through several iterations to find the proper size of the seepage phase. In order to do that, we have to click on this option here, Potential Seepage Phase Review. We will draw the boundary condition then, potential seepage phase. We'll draw it on the downstream face. Notice how the triangles represent a flux. The hollow triangles are a graphical reminder to you that this is a review phase, or in other words, SEEP-W is going to look at heads and fluxes until it finds the proper boundary condition between 0 flux and a head that is equal to elevation where the pressure is 0. We have assigned material properties to the regions. We have applied boundary conditions. So we have done the 3 parts of finite element analysis: the geometry, the material properties, and the boundary conditions. Clicking on our Verify button then, the verification says there's 0 errors, 0 warnings. This simply says that sufficient information has been supplied to the main solver such that it can compute results. It does not necessarily say the results are correct. It just says that sufficient information has been applied such that the solver can make some calculations. Clicking on the Solve button and then clicking on Start, we have solved for the solution. Clicking on the Results view, we have computed a line which is not a flow line, but it is a line of 0 pressure. And there are several things to highlight here. First of all, we have computed a seepage phase. If you go View Results Information, and we click on Nodes on the seepage phase, we notice that the pore pressure is 0. The pore pressure is 0. The total head is 0.45, which is equal to the y-coordinate. So all of these nodes here on the seepage phase have 0 pressure. Now we get to a point that is above the seepage phase, and the pore pressure now is negative. However, the water flux is now 0. So SEEP-W has determined the required size of the seepage phase. We can get an appreciation of the flow by looking at flow vectors. These vectors gives you a sense of direction, and the size of the vector gives you a sense of velocity or specific discharge. Notice the longest vector is at the toe. This is where the flow is the fastest, therefore it is represented by the longest vectors. The vectors are not scaled, they are just scaled relative to the fastest to the lowest. Notice that there is very little flow up in the upstream corner here, almost no flow at all. But most importantly, notice that there are some flow vectors above the line of zero pressure. And as in our paper experiments, the flow above the zero pressure line here represents flow in the capillary zone. The pore pressure here is a negative value. This is a line of zero pressure. Contrary to flow net construction, it is not a flow line. It is simply a contour where the pore pressure is zero. Moreover, as we have noted several times, there is flow where the pore water pressure is negative. Now, the further away we go from the zero pressure line, it becomes more and more negative. And recall our hydraulic conductivity function. The hydraulic conductivity goes way down when the pore pressure becomes highly negative. So there is little or no flow here. And that is because the pore pressure is highly negative. Let's turn off our flow vectors and draw contours. Say add, and the contour type will be total head. We are in the pore pressure category, and the parameter is total head. So here we see our contours of total head. We can label the contours. For the time being, I'm going to turn off my sketch objects to make it a little clearer. Draw contour labels. So here is a total head contour of 7, 6 meters, 5 meters, 4 meters, and so forth. We can change the font size of the flux labels. If you do not like where the labels are, they can be removed by clicking on a second time. Draw contour labels. Clicking on it at the second time removes the label. Now, total head contours are the equivalent of equal potential lines. Anywhere along one of these total head contours, the potential is the same, and so they are, in the context of a flow net, total head contours are equal potential lines. Total head equivalent to equipotential lines. In SEEP-W, we cannot draw a flow net, but we can say draw flow paths. And this is a path that a droplet of water would take from the upstream face to the downstream end of the dam. We can draw these lines wherever we wish, and clicking on the second time removes the line. And so this is a line where a droplet of water would start from the reservoir, travel through the dam, and exit on the downstream face. Notice that the flow lines are perpendicular to the equipotential lines. Let me back up here for the time being. I did not want a flow line there. The flow lines are perpendicular to the equipotential lines, as they rightly should be in this particular homogeneous case. So, with a little bit care in selecting where a flow line is, we can simulate an approximate flow net, but it is not a true flow net. In true flow net construction, we have stream channels. These are flow channels in a flow net construction. This diagram here does not produce flow channels that are of equal size like in flow net construction. Nonetheless, it does give an appreciation of where the flow goes, and the fact that they are perpendicular to the equipotential lines shows that we are getting a desired solution. One of the powerful features in SEEP-W is that we can graph the results in a variety of ways to help us interpret the results. Just to illustrate a few of the graphing options, we'll graph the pore pressure on the downstream face. We say draw a graph, and we have predetermined here a pore pressure graph. The location of the graph, let us say that the graph is on the downstream face, and notice that we have two options here. We can select some geometry item like the edge of a region, or we can drag a box over a section. In this case, I want to select geometry item. I will select the downstream face and say show the graph, and here in this particular case I would like to see the pore pressure rather than with the y coordinate. I would like to see it with distance, and we are looking here at the pressure head. So at the crest the pressure head is highly negative, and then we see where the pressure head is 0, that we have determined the seepage face. Once again, I want to draw your attention to View Results Information. You can click on any node or any Gauss region in an element to get specific information on a very detailed level either at the nodal level or at the element level. I'd like to draw your attention to another feature. Say draw a graph, add, say flux upstream face, our category is water flow, and the subtitle is water flux. We select this versus time. We don't really have time here, but this is a trick that we can pull if we say versus time, and then we check sum versus average value at the bottom here. We check this box here, and then set the location as a geometry item on this edge, the upstream face, show a graph. We see that we have one value here, and the value is 1.2 times 10 to the minus 5 cubic meters per second. This is the flow into the dam from the reservoir. Recall from our conceptualization that we had suggested that the flow should be very close to 2 times 10 to the minus 5. Indeed, it's not quite as high, but very close, 1.2 times 10 to the minus 5 cubic meters per second. We are going to come back and look at flux in another way, but that is one way to do it through the graphing function. So we have shown equal potential lines, which are total head contours, how to draw flow lines, how to graph certain parameters, how to look at flow vectors, and how to look at nodal boundary flux. Next, we will go on to adding a flux section, and it is another way in which we can look at the total flow that goes through the entire dam cross-section. Returning then to GeoStudio, going back to the define view, we say draw flux section. We'll draw one flux section. When we click OK, the cursor turns to a plus sign. The flux section should start outside of the cross section and end outside the cross section. Clicking the right mouse button completes the flux section. For illustrative purposes, let us draw another flux section. Draw flux section number 2. Click OK, and the flux section does not need to be a straight line. It can be a broken line. So now we have 2 flux sections. Reanalyzing the problem, we can now look at the flux quantities by saying draw flux sections. Sorry, first of all, we need to go to the results view. Say draw flux labels, and clicking on the section will give us the amount of flow that crosses this flux section. And in this particular case, it's 1.21, 1.21, and it's a steady state case, so and they must be the same as indeed they are, and the value is equal to 1.2 times 10 to the minus 5 cubic meters per second, the same as what we determined when we were looking out the flow that goes through the upstream face, which we did by the graphing. So there is another way to determine the amount of flow that goes through this homogeneous dam cross-section. Now we will go on and modify the cross-section so that we can simulate the effect of an under tow drain. We're going to have a tow drain here. We expect that the flow will come into the tow drain, something like this. And there are two very important points here. The fact that we can model the effect of the tow drain with a boundary condition. One of the features about numerical modeling is that we do not always need to include the real physical component. We can often simulate certain effects through a boundary condition, and you will see this several times throughout these presentations where we don't include the real physical component. We simulate the effect of that element in the cross-section through a boundary condition. So to begin with, we are going to do it with a boundary condition, and then I will show you how we can include the tow drain, but that the result is exactly the same. So going back to GeoStudio, open up the file, turn off the icon that shows the flux section, and this is where we had left off in the previous example. Now we want to simulate the effect of the tow drain here. So the first thing, say, draw boundary condition. This time we want to remove a boundary condition, and we want to remove the boundary condition on the downstream face. Once again, for clarity purposes, turn off the green ground surface line. We know that the water table is right here, and this is gravel, say. The tow drain being so pervious, in all likelihood, the water table remains at this elevation throughout the tow drain, so that we actually know that the pore water pressure here is 0. If we already know the pore pressure is 0, we can simply say, define the pore pressure here as 0 and get the solution without including the material for the drain itself. So we say draw a boundary condition, and notice that we had by default a 0 pressure boundary condition. We want to apply the boundary condition to a line, and we apply it to the line. And once again, we need to subdivide our region edge so that we can apply this boundary condition only over the extent of the tow drain. Click on Remove the boundary condition, turn on Snap to Grid, draw points, drawing a point at the edge of the tow drain at 40 meters. Now we say draw boundary condition, 0 pressure at the top of the tow drain, and we now have simulated the effect of the tow drain. Click on Verify. There are no errors and no warnings. Click on Solve, and we can now solve this problem. Going to the results view, we now have exactly what we expected. We have a zero pressure line that starts at the level of the reservoir and goes through the homogeneous section but ends up in the tow drain. Now, some of you may have expected this line to do something like this from your experiences with flow nets. In this case, however, this is not necessarily true because of unsaturated flow or flow in the negative region. If you turn on the flow vectors, notice that there is considerable flow that comes into the tow drain above the line of zero water pressure. So there is considerable amount of flow that comes into the drain where the pore water pressure is negative. To repeat, this is not a flow line. It is simply a contour of zero pressure. And so much of the flow that comes into the tow drain comes where the pore water pressure is negative, or in other words, once again, there is a capillary zone here. And we saw earlier in our paper experiments how we can get flow even though we have negative pore water pressures. Let us now go back to the define view and create a material for the tow drain. Before we can attach a material representing the tow drain, we need to draw a region. I'll turn off my boundary conditions and I will say draw regions, and I'm going to draw a region that represents the tow drain. Next, key in materials. We add a new material, call it the tow drain gravel. In this particular case, we know that the gravel will always remain saturated, so we do not need to define a function. We can simply say that the material has a constant hydraulic conductivity. In this particular case, it really doesn't matter. For illustrative purposes, let's say that the saturated hydraulic conductivity of the gravel is 1 meter per second. We'll select a color for the gravel tow drain. Then we can say draw materials. Now we have two materials in our drop-down list, selecting the tow drain gravel and moving over the tow drain region. Now, with our boundary conditions, we know that the total head everywhere in the gravel is equal to 0. Or say draw boundary condition. We need a new boundary condition. Say add tow drain, and the total head in the tow drain everywhere is 0. First of all, let's remove our boundary condition from the previous case. Say remove from this line. Now assign a tow drain boundary condition. This time we are going to assign it to a region. Moving over the region, we now have defined the boundary condition in the tow drain, and Clicking on Solve, we can reanalyze the problem. Moving to the results view, we see that the solution is identical to what we had before. We have now included the tow drain, but we could have modeled the tow drain with a boundary condition, a very important concept in numerical modeling. Now we are going to add a core to the dam. First of all, we're going to create a core where the hydraulic conductivity is 10 times less than the upstream shell and downstream shell. And then we are going to create another core where the hydraulic conductivity is 100 times less than the shell material. Going to GeoStudio and opening up SEEP 06. File, open SEEP 06. We have, in essence, the solution as to where we left off previously, but now we want to add a core to the cross-section. The first thing we should do is create some new analyses. We have one analysis here. Let's rename this one analysis, call it 1 homogeneous, homo for homogeneous dam. And when we tab out, then we have one analysis. We want a second analysis that is very similar to the first one. We can say clone this analysis, and let's rename it number 2 with core 10 times less. Let's create a third analysis and clone it again. This time it's number 3 core 100 times less. I will rename my second one core with 10 times less. So now we have 3 analyses, and we have introduced you to how to create additional analyses. Next, key in materials. Our general fill, which is the silt. Once again, it will be a very, very similar material, except that we will need a different hydraulic conductivity, and this time again say clone, and let's name this core with K 10 times less. And while we're here, let's clone it again and call this the core with 100 times less. And select some other shade of color other than green, perhaps this color here. So now we have 3 materials, but we need to have 2 different hydraulic conductivity functions. We can click on the ... and now we can once again clone this material, clone, and core K 10 times. And notice now that I can shift this curve down by simply altering this edit box here. When I type in here 1e minus 6, notice how the entire curve gets shifted down one order of magnitude. That's not very good. I meant 1e minus 6. And so now we have a saturated hydraulic conductivity of 1e minus 6. Cloning this material again, we get a third material that is 100 times less. And once again, what I want to do is shift the curve down one order of magnitude, 1e minus 7, and now the entire curve should just simply shift down one order of magnitude, as it properly does. So it's 1e to the minus 7. We now have three curves, 1e minus 5, 1e minus 6, 1e minus 7. Once again, if you hold down the control key, you can look at all three functions at the same time. So what we have done here is we have created three different functions. They all have the same shape, but the saturated hydraulic conductivity is different for each of the cases. We have three materials. For our three analysis, we have the homogeneous case. We have the second analysis with 10 times less, and we say draw materials. From our drop-down list, choose number 2, the light green material, and attach it to the core. Then go to the third analysis and say draw materials and select our third material and attach it to the core. And here is where the power of the GeoStudio system really begins to shine, and that we have done three analyses. Each analysis has a different property for the core material. As the rule is that the geometry is the same and the meshing is the same for all analyses, but boundary conditions and material properties can be different for each analysis. Another new feature then, when we go to the solve window, notice that all three analyses have not been solved. I can right-click and say select all. And what SEEP-W now will do is analyze all three cases one after the other. This becomes a very powerful feature when you have quite a complex situation and you want to make some changes, but you want to reanalyze all the different analyses. You can select them all, go for coffee, hit the run button and go for coffee, and it'll be done when you're back. Now looking at the results view, we are looking at the homogeneous case, which we looked at before. I'm going to turn off my flux section, turn off some boundary conditions here, and turn off my sketch objects. You still see the core because you are seeing the edges of the regions. Now we can say draw contours, and notice here in the tool bar that we are contouring total head. We have turned on total head. We can turn off the contours themselves and just look at the shading, or we can look at the contours without the shading. So here's our homogeneous case. I expected to see different results, but it looks like the solution is identical for all three cases. I made a very fundamental mistake, and I made this mistake to highlight what happens a lot. We need to go back to define, and in each of these cases, in these analyses here, number 1, number 2, number 3, we had assigned the right material, but in our materials here, we had not selected the proper function. Say key in materials. For material number 1, we had our hydraulic conductivity function for the general fill. For the second one, we should have selected the second function, which we didn't do. This is quite a common mistake and something that you need to be quite careful of. For the third material, we need to select the third function. So, establishing the materials, and then you need to attach the appropriate function to the materials. Now we can reanalyze all three cases again. Once again, right mouse click, select all. You can immediately see how convenient it is to reanalyze all the cases at once. And now when we go to the results view, we have for the homogeneous case exactly where we left off previously, but now notice when the core is less permeable, or the hydraulic conductivity of the core is less than the shell material, then more of the head gets dissipated with the flow through the core. And when it is 100 times less, then even more of the head gets dissipated in the core. Almost all of the potential from the reservoir gets dissipated in the core itself. It's rather interesting that if we turn on flow lines, let's draw a few flow lines, draw flow paths. Once again, notice how the flow paths are perpendicular to the equipotential lines. This is true both in the saturated and in the unsaturated zone. Notice in the upstream shell, almost no head is dissipated because it is so much more permeable, and consequently the zero pressure line is almost horizontal. That is because here is the first equipotential drop, so there's almost no head loss by flowing through the upstream shell. Almost all of the head is lost within the core itself. Very little of the head gets lost by flow in the downstream shell. This brings up an important point, that when we have material contrast, even one order of magnitude has a very significant effect on the flow regime. In this particular case, we have 2 orders of magnitude difference, and we see that the core almost completely dominates the loss of the potential from the reservoir, or all of the energy is lost by flow through the core. So you can see how easy it is to analyze various cases all within the same file, simply by establishing different material properties, creating more than one analysis, and then assigning different properties to the various analyses. And this is one of the powerful features of GeoStudio in general, and in particular for all the finite element analyses. Now I want to draw your attention to the effect of the core and the flow lines, which we have already looked at. Once again, we see there is an awful lot of flow in the unsaturated zone. And here are flow lines in the unsat zone. and once again the flow lines are perpendicular to the equipotential lines. But one of my reasons for bringing this up is that this illustrates why we do not concentrate on flow nets. It would be nearly impossible to create a flow net for a situation like this, and the reason for this is that because the hydraulic conductivity is a function of pore pressure, and the pore pressure changes a lot, every element in the negative pore pressure zone has a different conductivity, and you know that when we draw flow nets, we have to scale drawings to match the contrast and hydraulic conductivities. In this case, where every element has a different hydraulic conductivity, it would be nearly impossible to draw a flow net. So this is one of the reasons why we do not draw flow nets, because they are only possible in very unique situations, usually only in homogeneous situations. Now, there is a tendency when people start using SEEP-W to say that I don't understand anything about unsaturated flow, and all I want to do is to do a very simple analysis, and therefore I will simply assign my material a constant hydraulic conductivity rather than specifying a function. In essence, what is being said is that I will have a horizontal function. So this is minus plus pore pressure conductivity, and what we are saying is that we will have no function at all. It will be a constant value. Unfortunately, this is one of the worst things that you can do. Defining no function for an unsaturated flow problem is worse than a rough approximation of a function. We illustrate this in the file SEEP-07. Going to GeoStudio, File, Open. SEEP-07. We have created a material here, SAT only. We have selected SAT only, so we don't need to define a function, and given it a saturated hydraulic conductivity of 1 to the minus 5 meters per second. And looking at the homogeneous case, we see that we get a lot of flow high above the line of zero pressure. The equipotential lines are almost the same as what we got when we had a function, and so the pressure distribution is not all that reasonable, but the total flow through the section is way too high. There's too much flow. Too much flow high up in the section where the pore pressure is negative. So the message here is that no function is probably one of the worst cases that you could specify. Any approximation of a function, regardless of how approximate it is better than no function at all. So I would urge you not to make the assumption, I don't understand unsaturated flow, I just want to do a simple analysis, therefore I will just use a constant for my hydraulic conductivity, and that is not a good idea. You should always have a function, even though it is just an approximation of a function. This brings us to the end of our illustrative example of flow through a homogeneous dam, and then a dam with a toe drain and a dam that has a core where the core has several different hydraulic conductivities.